Okay, for this problem, you're going to need your reference table again, because you're going to need this coefficient of friction chart. This is similar to the problem we did earlier. I want to make a quick distinction here with this problem. It says a moving man pushes a 25 kilogram steel box on the steel floor of a moving truck. It's important to note that this is not a truck in motion, that this is a truck used for moving stuff. And I think that's a really weird choice of words to put into a question like this. All right, the first thing we're going to do is going to calculate the weight of the box. That's really easy. We're going to go ahead and use our force of gravity equation, which is equal to the mass of the box times little g. The value of little g, as we know, is 9.81. You can roughly equate that to 10 to make your math easy. But anyway, the force of gravity in this problem is going to be force of gravity is equal to the mass of 25 kilograms multiplied by 9.81. Force of gravity will be roughly equal to 250, but for a more precise answer, I'm just going to multiply those together and you're going to get 245.25, and the unit will be newtons. So that is the weight of the truck. All right, question 2, we need to set up the friction equation just like that problem we had on the last page. We have to look here what this object is. So it's at rest right now. It's not moving. The truck is a steel floor truck, and the box is steel on steel. So, sorry, the box is steel on the floor, the truck is steel. So we need the steel on steel mu. We'll be doing this. And we, in this case, do not want the kinetic this time because the object is standing still, right? So this is what we're going to use from rest. And this is what we would use if it was moving. Just remember that kinetic means moving, right? So that's how you know which one is which. But steel on steel is 0.74 as the mu. So in this case, the force of friction will be equal to the force of gravity of 245.25 newtons multiplied by the mu of 0.74, and that gives me force of friction of 181.4. It's actually 0.485. That's the amount of friction you would have to overcome in order to get this box to move. So the force applied would need to be anything greater than 181.485. If you pushed it with 180, it wouldn't move. If you pushed it with 181.48, it wouldn't move. If you pushed it with 181.485, it would move, right? So anything greater than 181.485. All right, the next question is saying, number 3, if this much force is applied once the box starts moving, what is the net force on the box? And the reason why they're asking that question is because once the object starts moving, we can no longer use this force of friction static anymore. We have to switch over to the moving friction, right? So we need to recalculate the force of friction now. And for that, I want to draw out this free body diagram. So I have this steel object that is riding on a steel surface, and I like to draw all of that information on the free body diagram to show me what's going on, right? So it's a level, flat steel surface. There's a 25 kilogram box sitting on it. Someone comes along and pushes it, and they want it to move. So we calculated the force of static friction as 181.49. I'm sure that the answer here is actually supposed to be 182. That's how the math looks like it's supposed to work out. So anything greater than 181.49, and the object will start to move. Once the object starts moving, the coefficient of friction will change, right? And then so what's going to wind up happening with that is that the force applied is going to stay the same, but the force of friction will get smaller. So once the force of static friction is broken, this force vector is going to become just a little bit shorter, right? And so what's going to wind up happening is the forces will be unbalanced and the object will start to accelerate to the right. So you will have a net force acting on this object. Let's calculate what that net force will be. So the force of friction will be equal to the force of gravity, which is 245.25 multiplied by the new mu, which is 0.57 for steel on steel moving. This is multiplied by 0.57, which comes out to force of friction equals 139.8, let's say, in the negative direction. So instead of this force of friction being 181.485, it is now going to be 139.8 in the negative direction, right? So we're now having an unbalanced situation. We have 181 pushing on the right, and we have only 140 roughly opposing it, right? So we have to find the difference between those two numbers. So you're just going to take your, let's just call it 182, and we're going to subtract our 140, and that's going to leave us with a total of 42 in the positive direction, right? So basically what happens here is 139 of this cancels out 139 of that, 140 of that, and so we are now left over with an overall force applied of 42 newtons acting to the right, okay? So we don't want to change the free body diagram and erase the vectors, but just to give you a visual, what wound up happening here is that this vector has gone away. Ultimately, there is no more force opposing it. I mean, it's there, but just to show you what's going on. And then overall, the force applied has been shrunk, right? So it may look like something like that now, maybe even a little bit smaller. And so now you still have a free body diagram showing gravity, and you still have a little bit of an unbalanced force acting to the right, okay? Question 4 asks you to do something with this information. So now we have this object that is 25 kilograms, and we have a force acting on it to the right of 42 newtons, and it's going to ask you what the acceleration of this object is. You need to know Newton's second law, which is force is equal to mass times acceleration, right? And the mass of this object is equal to 25 kilograms, and the overall force applied is equal to 42. So you're going to set up the equation like that. You're going to divide by 25 in order to cancel this, and you're going to divide by 25 over here, and your acceleration will be equal to 42 divided by 25, which is 1.68, so we'll just call that 1.7, and then the unit of that is meters per second squared, and it's accelerating to the right, so we give it a positive there. So it's positive 1.7 meters per second squared. So if left unchecked, this object would continue to accelerate at 1.7 meters per second squared to the right. Next question is asking, how long will it take the box to move 6 meters? Okay, so sure that they gave you the 4 kinematics equations, d equals VIT plus 1/2 AT squared, VF squared equals VI squared plus 2AD, right? You have a reference table that has that information on it. I really like I really like to do this. I actually forget how I used to teach it, but I just looked at it real quick, and it's velocity final squared is equal to velocity initial squared plus 2 plus acceleration times distance. That's an easy equation to solve, right? So the distance here is 6. My acceleration is 1.7 times 2, so that's going to be 2.4. I'm sorry, 3.4. So, and my initial velocity is 0 because it started from rest, right? So this just says that my velocity final squared is equal to 3.4 multiplied by 6. So 3.4 times 6, 3 times 6 is 18, and 0.4 times 6 is 2.4. So velocity final squared is equal to 20.4. I'm going to take the square root of this side and the square root of this side. That cancels out the square. So that's my velocity final is equal to the square root of 20.4, which is 4.5. So what that means is how fast is it traveling at the end of its motion to 6 meters? It's 4.5 meters per second. Now, how long will it take for that to happen? Well, it started at 0 and it ended at 4.5 meters per second at a rate of 1.7 meters per second. So all you got to do here is take the overall velocity of 4.5 and divide it by 1.7. So 4.5 divided by 1.7 gives me 2.64. And how that looks in an equation for you, again, if you have your kinematics equations, it says that velocity final is equal to velocity initial plus acceleration times time, right? So we know that my velocity final was 4.5 meters per second. My velocity initial was 0 plus my acceleration of 1.7 times the time, right? So the 0 cancels out, goes away. This becomes 4.5 meters per second is equal to 1.7 times time. So it becomes 4.5 divided by 1.7. And that means that time is equal to, what did we say, 2.6. Let's call it 2.65 seconds. So the question is saying how long will it take that? That's going to be 2.65 seconds, or if they're looking at sig figs, it would be 2.7 seconds. Okay. Question 6 is a bit weird. I don't love this question so much. I would challenge this question if I were you with the teacher, because it's vague and it's not asking you to redo the math, and you're going to have to redo some of the math on this to get the answers. Some of them are easy and some of them are going to require you to redo all of the math we just did. All right, so I'm going to try to answer these with you without doing that. The box was twice as massive. How would it affect the weight? Well, the weight would be twice as much. If the force needed to get it started moving would be larger because the box is larger. But even though the force required to get it moving would be larger, the acceleration once it started moving would be the same, because the relationship between mass and friction is linear. So as mass goes up, the force of friction goes up the same amount, right? And the coefficient of kinetic friction, that would also stay the same, because that is a known value of steel on steel. Even though the amount of weight goes up, the force of friction will increase, but you won't change the coefficient of friction. The only way to do that would be to like edit the surface somehow. Like if you added glue, or if you added like soap or like oil, you would change the coefficient of friction. But most physics classes at this level are not going to ask questions like that. All right, hope this was helpful. Sorry this video was so long.